Well, we're back at the physics video lecture. It is Physics 107B video lecture 24. We're talking about special relativity, and we ended up with time dilation, length contraction, the Lorentz transformation. I'm going to go from there straight into relativistic mechanics and dynamics before returning to a lot more having to do with the Lorentz transformation. So yeah, we'll do relativistic mechanics. And what we want to do is get the principle of least action and put together the Lagrangian and Hamiltonian methods and that formulation. So we're just going to start with, recall, the moving clock runs slow for the person who's watching it move. Okay, the moving clock runs slow, and what we can introduce is an idea of the proper time of the clock. Tau is going to be the integral t1 to t2 root 1 minus v squared over c squared dt. So that is a moving clock at any instant in time. So at any instant in time along its trajectory, we can instantaneously say, well, it's in an inertial frame, right, for that infinitesimal amount of time, and we're just integrating those up. This will always be smaller than the time we read on our own clock as we're observing the moving clock. So that's the idea there. So yeah, we have this d tau is equal to root 1 minus v squared over c squared dt. So this is going to be invariant with respect to a Lorentz transformation, as we'll see more later. But right now what we want to do is put together a principle of least action. Okay. So in classical mechanics, or let's say in Lagrangian mechanics, this is all classical. Lagrangian mechanics, we had the variational principle, L dt, t1 to t2 was equal to 0. And what did that supply us with? Well, first of all, independent of coordinate system. And that gave us, here, block this off. That gave us equations of motion. Okay. So we want something similar in the relativistic case. It's going to be constructed out of this right here. And what we'll do is match it up for a free point particle in the limit of small v, okay? Good. So the note I wanted to put here was free particle L is t minus u, but the free particle, we don't have that, so it's just a half mv squared. We're going to try to match our relativistic Lagrangian up with this. Okay. So consider L relativistic being equal to minus alpha c root 1 minus v squared over c squared. This is a 1 minus. So c b tau is a length. Alpha, this is the speed of light. Alpha is a to be determined constant. Or v over c much less than 1. Or Lagrangian would be minus alpha c 1 minus 1/2 b squared over c squared approximately would be minus alpha c plus alpha c b squared over 2c squared. And now we can determine what alpha is. If alpha is mc squared, mc, then we have mc squared cancels the c squared, then we have mv squared over 2. So alpha equals m times c, and that gives us, like I said, mc squared over 2c squared gives m over 2 v squared. So this one does the trick, and L relativistic for a point particle is going to be minus mc squared root 1 minus v squared over c squared. Okay, now there's also the relativistic Lagrangian. Yeah, I'm going to put some other stuff up here right now as well. None of this is being proved that rigorously because in this endeavor you actually have to draw the consequences and see that they match up. So I'll also put also for a charged particle in an electromagnetic field, we have L relativistic is equal to minus mc squared. So there's the free part, 1 minus v squared over c squared, plus q vector potential, not dot or dot v, plus q scalar potential minus q scalar potential. Okay, so I want to put a box around both of these. So this looks like something we worked on back in mechanics, okay? Except what did we do in mechanics? We actually looked at the non-relativistic one. I'm going to add that here. So in mechanics, we had studied this thing here, and we took half mv squared plus q a dot v minus q scalar potential. We called it feedback then. Yeah, so in mechanics we had worked with this thing and we had found its equations of motion. So that's why I'm going to list all these things right now, and that will remind us what we have to do with this thing here. Okay. Let me go ahead and erase all of this. Down here. Good. So yeah, I'm talking about this one right here now. So this is actually an important discussion before we go back to these relativistic ones. Good, so in mechanics we had taken this Lagrangian. So we found that the Euler-Lagrange equations, which were d over dt, dl d, let's say r dot, which is v. We could, for what we're going to do today, let's go ahead and call it dv minus dl dr equals 0. Those Euler-Lagrange equations on this object here, what did we have? We had A was a function of position, B was a function of position. These gave us m r second derivative equals QE plus Q V cross B, where B was equal to the curl of A. Okay, yeah, so we did this before, and this was the this was non-relativistic, of course. I don't know if we mentioned it at the time. Non-relativistic. We didn't explicitly say v much less than speed of light. The speed of light wasn't even in here. Okay, but yeah, so we had done this, and so we had that whole formalism. In particular, we also then found the Hamiltonian. So I'm just going to put those things down. So I'll just write furthermore. We had energy E. I'm going to have to get a different letter for the energy. Maybe I'll use this kind of E. So energy E was equal to dl dv dotted into V minus L. We usually write dl dr dot, dotted into r dot, or the summation over, sum over dl dqi dot qi dot minus L. Right. That's the energy. And energy expressed as a function of P equals dl dv. Okay, that's my shorthand for saying energy, if I express it in terms of P instead of V, is equal to the Hamiltonian H of in this case, R and B. So that's the program we want to actually go through with on our free-point particle, first of all. So this whole Lagrangian thing. This is what we've done in the past. We have this Lagrangian. We showed that it gave these famous equations of motion. And then we could form the energy according to this recipe. And then if we express the energy in terms of the momentum instead of velocity, we get the Hamiltonian. I'll put that here. The Hamiltonian. So our goal is to go through some of this formalism and then actually do the charged particle, the relativistic charged particle, in the constant E field, which will give a really interesting result. But we got to work our way up to that. Okay, is that clear? That should be somewhat clear. This here is just the Lagrangian program that we've studied in the past. Now we have a relativistic Lagrangian for a point particle, and we're going to run through this program right here, see what happens. Okay, good. So I'll erase everything and then start up with this guy again. Okay, where were we? So we have minus mc squared root 1 minus b squared over c squared. That's our Lagrangian, and the first thing we're going to do is get the momentum. Then we can number these things. So here we're going to have P is equal to dl dv, where v is a vector. So yeah, this is now the speed of the particle, not a translational speed between two coordinate systems. Okay, this is the speed of the particle. So we have v squared equals plus vz squared, right? You could also call it r dotted into itself, dx, dt, and so forth. So yeah, let's do that. We have minus mc squared 1/2 root here in the denominator, 1 minus v squared over c squared. Derivative with respect to v, so that would be minus 2 vector v over c squared. Right, the individual components, you do them component-wise, you get 2vx, 2vy, 2vz, so that I'm taking all three derivatives at once. Minus signs cancel. We have 2's cancel, mc squared over c squared, v divided by, so those cancel as well. So what do we have? P is equal to mv over root 1 minus v squared over c squared. So first thing we see, of course, the dimensions are right. We also see that in the limit of small v, formally sometimes people just say the limit as c goes to infinity, or, v over c, very small. We get back to the standard linear momentum, m times v. And we also see, not for the first time, this v as, or c as being the speed limit in nature. Okay, in other words, we can't get v equal to c because our expression becomes undefined. So good, there's the linear momentum. Note P goes to m times v when v over c less than 1. Anything else to say about that? Let's see here. Okay, good. This next one needs a little room. Let's see here. So part 3, force is just given by dp dt. Okay. This time we have to be serious about this and not say m times our second derivative, so this is really the force, the derivative with respect to time of the linear momentum. So that's an interesting one. We have dp dt is equal to, we can just, we got a product rule here, m dv dt over this root. But of course we're not done, so we have plus mv, and then the derivative of this 1 over square root, derivative of that gamma. So with respect to time, that would be negative 1/2, and then this thing in the denominator to the 3/2, 1 minus b squared over c squared. 3/2 power, and then we have minus 2 over c squared v dotted into dv dt, okay? Because we're taking a time derivative, so we've got that chain rule there. So minus, this is a v squared is a v vector squared, so minus 2v dotted into v dot, this is v dot v. So yeah, that's what we get, and let's simplify it. Yeah, this has some interesting consequences. Let's make sure we, okay. First, let's just clean this up a bit. dv dt, the root. This one here, let's see what happens. Minus signs cancel, 2's cancel. We have mv times v dotted into dv dt. 1 minus b squared over c squared, 3/2. So they're very different behavior depending upon whether v and the derivative dv dt, whether they're perpendicular or whether they're parallel to each other. If they're perpendicular, this whole term drops away. So, and if they're somewhere in between, you get a mix of them, but the two cases, perpendicular and parallel, are pretty interesting. So, if v dot dv dt is equal to 0, so that's the perpendicular case, then this drops away and we just have the first part of the formula. If they are parallel, this thing simplifies quite a bit, but we have to write it out first. If v is parallel to dv dt, then we can simplify this, then v times v dot dv dt, it's going to be a vector, but I'll just give its magnitude. Will be v squared dv dt. Okay. If they're parallel. It's still a vector, but its magnitude is v squared dv dt. And what we do now is get a common denominator for that thing. So now now dp over dt over a common denominator of 1 minus v squared over c squared. physics will be m dv dt plus m v dt. And because I'm looking at the parallel case, we're going to get this cancellation. So m dv dt minus b squared over c squared plus m dv dt b squared. Where's my c squared? I must have lost the c squared up here. I did. It's right there. C squared. I lost that right there. C squared. So those will go away against each other, and you get is equal to okay. This is interesting because these behaviors are quite different. Yeah, so we're comparing the square root to the same quantity to the 3/2 power. So if you're going to take the ratio, if you're going to take the ratio of the acceleration to the mass the way we usually do for force, okay, you're going to see quite different behaviors depending upon these two conditions. So this was the parallel, this is the perpendicular, this is the parallel. And this was discovered early on when they started doing charged particle experiments, because there was a big difference in the behavior if it was linear or if it was a circular motion problem. So much so that they actually had expressions for a longitudinal mass and a transverse mass, okay, which we don't talk about anymore, but formally they're in there because, yeah. Because if, you could have your dv dt and you could take this m divided by this square root here as your mass, and compared to the m divided by this thing here to the 3/2 power as your mass. Okay, so good. We have that. Let's see what else. So yeah, the big difference between these two. Okay, next. I'll put this as a so note the different ratios of force and mass. Like I said, that was encountered experimentally. Okay, our next topic is to go back to the progression of the Lagrangian expressions there. We want to calculate the energy. It's not up here anymore, but that's what we'll do next. Okay, so next, the energy. And I'll use this E here, and we know that is dL dV dotted into V minus the original L. So this is the mv over root dotted into V minus negative mc squared root 1 minus v squared over c squared. So if we simplify that, we have mv squared 1 minus v squared over c squared plus mc squared. We're going to go ahead and put it on a common denominator, which will give us 1 minus v squared over c squared. And you can see the mv squared cancels mc squared minus v squared over c squared. So that goes away and we're just left with mc squared over root 1 minus v squared over c squared. So that's the famous E equals mc squared. Or E equals mc squared. And we see that when the speed is 0, we still have what's called the rest energy. And that energy is no longer a quantity to which we can just add arbitrary constants, okay, in the relativistic regime. So note, rest energy is just mc squared, but this is the energy according to its systematic definition here of a point particle. With the full Lagrangian, we could actually get the energy of a charged particle in the field too. Maybe we'll do that. Okay, any other comments on this one? Ah, yes. This is good. We have P up there. We don't have P up there. Yes, we do. P was this. So since that was P, we also have something else also. We can take this E over C squared. Yeah, we can take the E over C squared, or actually the E over MC squared. Okay. So E over C squared, put the M there, multiply it by V, and we have the momentum. So that's a really useful relation between momentum, velocity, and energy. Yeah. Divide this by c squared, you've got m over this, multiply by v, you've got p. Okay. Good. Okay, what's next? Okay, next we want to get the Hamiltonian. This one just requires a bit of algebra. So next, the Hamiltonian. Good. So really the Hamiltonian is just the energy where we express the speed in terms of the momentum. There's not going to be any position in here, it's a free particle. So what we'll do is the following. We need to get v squared over c squared, so we have P is equal to mv over 1 minus v squared over c squared. p squared actually p squared over mc squared, right? Or is it m squared c squared? Okay. That's right, m squared c squared. Because p over mc is equal to b over c root 1 minus b squared over c squared. And if I square both sides, I get my b squared over c squared. And b squared over m squared c squared is equal to b squared over c squared 1 minus b squared over c squared. That means good. So yeah, we'll just plug that in. So now what we'll have is h squared is equal to m squared c to the 4th, 1 minus, and this b squared over c squared is b squared over m squared c squared divided by 1 plus m squared c squared. But this simplifies nicely because you get the 1 plus minus that, so you end up with m squared c to the 4th. You got a denominator, of the denominators you got a 1, and the numerator you've got 1 plus b squared m squared c squared. So we can multiply that out and get our answer. Okay, so now h is going to be, so this is the Hamiltonian, square root of m squared c to the 4th plus c squared p squared. So now we have the Hamiltonian. And we've learned something new here because apparently, at least it's not inconsistent to have a massless particle. When m is equal to 0, we still have this energy here, c times p. So I'll say next, massless particles, question mark. So what we're going to do here, finally, is take the Hamilton's equations. So first, we know we have P dot is dH dr. Remember, there's a point particle, there's position r. And r dot is equal to, actually this one gets a minus sign, dH dP. So those are Hamilton's equations. This, of course, is equal to 0. And we end up with P is equal to constant. And of course, we already know what P is. Okay. Free particle, constant velocity. But this r dot equals dH dp is interesting. So we get an r dot, we get dH dp, which is 1/2 root m squared c to the 4th, c squared p squared. And then since it's with respect to time, no, I'm sorry, it's not with respect to time. R dot 1/2, it's with respect to p, so we have 2c squared p vector. Now this is m equals 0 this time around. So m equals 0, we have c squared p over c times p, which means we have c momentum over its magnitude. So that's interesting because that's a unit vector pointing in the direction of motion, and the speed here is the speed of light, see? So we have massless particles move at the speed of light. Speed of light. Just as a, relativistic consequence. Now, if m is not equal to 0, we are in fact just going to regain something that's no longer on the board. Let's see. Yes, it's actually here as well. 2's cancel. R dot would be c squared p over e, and that's the expression we had there a little while ago. Okay, you'll find it up there. In other words, what we would say is v is equal to c squared p over e. We had p was e over c squared times v, right? So the m equals 0 case gives us this. The m not equal to 0 is just a consistency check. Okay, so everything is consistent and working out. Okay. I think I'll gather all these things together. On one board. So, summarizing for the moment, we have that free particle relativistic Lagrangian that does deliver the goods. So P is mv root 1 minus v squared over c squared. Energy 1 minus v squared over c squared. And then the relation between these two, energy over c squared, energy over c squared times v is equal to p. That's the one I was just mentioning. And then we also have h is equal to root m squared c to the 4th plus c squared p squared. That's a nice set of results. Okay, so what are we going to do next? So next we're going to use these facts. I had a couple more up there. First I'll write this down. So next we want to do the following. dp dt is equal to qe plus q b cross b. And we want to solve for dp dt is equal to E with constant field. So that'll be an interesting one, because from what we've already seen, the momentum can't increase out of bounds, or the velocity can't increase out of bounds. But yet this is a constant force, so for t goes to infinity, in non-relativistic mechanics, we would have velocity go to infinity, energy go to infinity, and so forth. We'll see what we get on this one. For t goes to infinity, it's going to be a constant force, QE. Right, it'll be a uniform field, constant force problem with no B field. Yeah, I was about to write down again. I had the fully relativistic Lagrangian, but I already put it down earlier in the hour, and the expression for the energy. I will make one point here. So in the field, and what I'm talking about are E and B fields, this energy, and it's not that hard, you guys could actually do that on the side, so to speak. The energy is turned into mc squared over root 1 minus p squared over c squared plus q times v. Okay. So what's interesting is we can still use this relation for a charged particle in a field if we equate this energy only with this part. This would be the total energy. We can still use this as basically a kinematic result of sorts, even though it's dynamics, but free particle. That result, it will still hold true in this scenario as long as we identify this energy with this first part right here, which is what we're going to do. Okay, good. I think that's about it. Yeah, I almost forgot. There is a homework that I forgot to write up last time. So these are our problems. I could assign a little more with this stuff, but this was actually prior to that and out of chapter 12. So I'll put it here. So homework chapter 12, problems 9, 10, 17, 30, 33, 36. That's the last set, unless we do something with this, but this we'll be doing together. So this will be the last set, these problems. Okay, good. See you guys next time.